Section: Introduction. In this section, we explore the predictable scaling behavior of advanced AI systems like GPT-4, Claude, and Gemini. Understanding how these systems evolve in capability is crucial for making informed decisions about their development and use. While we have established scaling laws that describe the relationships between various factors like parameters, data, compute, and pre-training loss, predicting specific abilities as these systems scale up remains a challenge. Previous studies have shown that the performance of AI models on standard tasks can sometimes change unexpectedly as they grow in size. This unpredictability may be influenced by how researchers analyze the results, such as the metrics they choose to use. Some researchers suggest that we can predict a system's capabilities once its pre-training loss reaches a certain level, while others argue that looking at results across multiple tasks gives a clearer picture of how performance scales. We step back and ask why it's hard to predict specific abilities as AI systems scale up. One new challenge we identify is that common metrics used to evaluate these systems, like accuracy and Breyer score, may not accurately reflect how the system's performance changes with scale. These metrics compare the model's output with a few specific incorrect answers, which can make it difficult to predict how well the system will perform on different tasks as it grows. To better understand this issue, we study how the probability of choosing incorrect answers changes as the system's computational power increases. Our findings shed light on why predicting individual task performance is tricky, while scaling laws based on pre-training loss remain more consistent. Understanding these factors is crucial for designing evaluations that can effectively track the progress of advanced AI systems. To study how different AI models perform on various tasks as they scale up, we collected data from a wide range of model families and multiple-choice NLP benchmarks. We used a standardized evaluation tool to ensure our results were comparable to previous studies. We focused on model families with varying sizes and training data, such as Pythia, Cerebra's GPT, Olmo, Insight, and LLM 360. These families were trained on different amounts of data and had varying numbers of parameters. We evaluated their performance on popular NLP benchmarks that test comprehension, reasoning, and general knowledge. By analyzing how these models perform on different tasks as they scale up, we aim to gain insights into how AI capabilities evolve with increased computational resources. Section Summary. In this section, we explore the challenges in predicting specific downstream capabilities of AI systems as they scale up. We identify that common multiple-choice question answering metrics like accuracy and Breyer score degrade the statistical relationship with scaling parameters due to their reliance on comparing the ground truth output with specific incorrect choices. By studying how probability mass on incorrect choices fluctuates with increasing compute, we shed light on the unpredictability of individual downstream metrics and emphasize the importance of understanding factors affecting downstream performance for tracking the progression of AI capabilities reliably. Section: Performance Metrics. In this section, we utilized three common metrics for multiple-choice tasks: accuracy, Breyer score, and probability mass on the correct choice compared to all available choices. We then delved into the challenges of predicting downstream performance. Performance on multiple-choice benchmarks is typically evaluated using accuracy, Breyer score, or probability mass on the correct choice out of the available options. These metrics are calculated based on the negative log likelihood of the correct choice for a specific benchmark sample. It's important to note that these calculations are done per individual data point and not averaged over a dataset. The negative log likelihood is computed over the model's vocabulary, and the probability mass of the correct choice is then determined with respect to the model's vocabulary. Next, probabilities are adjusted to only consider the available choices by masking out invalid options and normalizing the probabilities accordingly. This distinction between the model's token space and the available choices in the benchmark is crucial for predictability. The normalized probability masses are then used to compute standard downstream metrics. We observed that as we progress through these transformations, the predictability of performance decreases with scale. To assess this impact on predictability, we examined how the scores correlate with pre-training compute and how this correlation changes as we move from log likelihoods to probabilities related to the model's vocabulary and available choices, and finally to accuracy or Brier score. By analyzing the correlation values between pre-training compute and scores for each sample in the benchmark, we observed shifts in the distribution of correlation values across different metrics. Visualizing these distributions allowed us to understand the relationship between scores and compute for each combination of model family, benchmark, and performance metric. We used various correlation metrics and found consistent results across different benchmarks. The transformations from log likelihoods to probabilities to standard metrics like accuracy impacted the correlation between scores and compute. These transformations led to a decrease in the correlation values, indicating a change in predictability. Overall, our analysis revealed a consistent pattern in how these transformations affect the correlation between scores and compute, providing insights into the predictability of performance across different benchmarks and model families. Section Summary. In this section, we explore how different transformations in computing performance metrics impact the predictability of downstream performance. By analyzing correlations between pre-training compute and scores using various correlation metrics, we find that transforming from log likelihoods to probability masses on available choices decreases the correlation, with accuracy showing the lowest correlation. This degradation in predictability is consistent across different benchmarks and model families, highlighting the importance of understanding the impact of metric transformations on performance predictability. Section. Probability masses on incorrect choices cause unpredictability. In this section, we explore how the distribution of probability masses on incorrect choices can lead to unpredictability in assessing AI models. We investigate how the correlation between scores and computational power is affected by this mechanism. The metrics accuracy, Brier score, and the probability of choosing the correct answer all rely on how the model's probability mass is distributed among both the correct and incorrect choices as computational power increases. For instance, if the model assigns a probability of 0.4 to the correct choice in a four-way multiple-choice question, the accuracy will be 1 if the remaining probability mass is evenly spread across the incorrect choices, but it will be 0 if the mass is concentrated on a single incorrect choice. We visually demonstrate how the performance metrics change when the probability mass on incorrect choices is altered. When evaluating performance based on the probability of choosing the correct answer or the accuracy or Brier score, the relationship between the metrics and computational power becomes less clear. Unlike metrics that focus solely on the correct choice, these metrics can lead to various values of the probability of choosing the correct answer or the model's probability distribution, making it challenging to infer computational power accurately. We observe that the Brier score, which aims to provide more continuous scores, is less variable than accuracy when the probability of choosing the correct answer is known. However, it cannot fully capture the information about the model's probability distribution that is lost when transitioning to metrics based on the choices made. Our analysis highlights the importance of considering the probability mass on incorrect choices when predicting performance on multiple-choice tasks. Understanding how this probability mass fluctuates with computational power is crucial for accurate performance predictions. We suggest that fitting scaling trends for each incorrect choice per sample could help predict changes in metrics like accuracy or Brier score. While our study shows a positive relationship between the probability mass on correct and incorrect choices for various benchmarks, predicting these trends accurately for each choice and sample remains a challenge. Future research should focus on fitting and extrapolating these scaling trends to improve the predictability of AI model evaluations. In conclusion, we reveal how the distribution of probability masses on incorrect choices introduces unpredictability in assessing AI models. Our findings have implications for designing evaluations that are more reliably predictable as computational power scales. We encourage further research to advance the science of scaling predictable evaluations for AI systems, especially for complex model capabilities. Section Summary. In this section, we explore how the probability masses placed on incorrect choices impact the unpredictability of AI model performance metrics like accuracy and Breyer score as compute increases. We demonstrate that the distribution of probability mass on incorrect choices significantly influences the model's overall performance, highlighting the importance of considering not only how mass concentrates on correct choices but also how it fluctuates on incorrect choices with scaling. Our findings suggest that understanding and predicting the scaling behavior of probability masses on both correct and incorrect choices could lead to more reliable evaluations of AI models, especially in complex tasks like multiple-choice question answering. Section. Direction 2. Predicting benchmark performance a priori. In this section, we discuss why it is challenging to predict how well a multiple-choice benchmark will perform using metrics like accuracy and Breyer score. Our analysis requires having access to scores from various model families over different levels of pre-training computational costs, without using backtesting as suggested by previous studies. A good predictive model should be capable of foreseeing changes in standard metrics such as accuracy or Breyer score ahead of time.